So let's continue our discussion of different glass strengthening mechanisms. And in these cases, we're going to get into a particular type of stress that we apply that will allow us to strengthen the materials. So the first one I want to talk about is thermal tempering. So this process is basically, if we think about it, this diagram here is thinking about it in the terms of window or sheet glass. So basically what we do is we take that window or sheet glass, but it can be other forms as well, and we heat it above the glass transition. And we know that glass transition is a place where that allows for the rearrangement of the network in a glass, right? It allows us to go in kind of the more rubbery state that we see up here above the glass transition. So we heat it to above the TG, and then what we do is we hit it with jets of cool air. So you see that like we have they call it an air quench here. And what that does is it rapidly cools the glass. More specifically, it rapidly cools the exterior of the glass, right? So you have a very cool surface. However, the interior of the glass remains fairly hot because we have this air, and the glass itself is a poor conductor of thermal energy. So the interior remains hot, and so it cools at a much slower rate. And so what that does is, if we go back to this specific volume curve that we first discussed, and we look at the glass material, so these two curves here, you'll notice that they have fast cooling and slow cooling. Well, if we cool the glass fast, and so the exterior of the glass is like this one, and what we see there is that this curve is above this one, which means it has a higher specific volume, right? So it basically doesn't contract as much when we fast cool it, as opposed to the interior glass, which cools at a slower rate, kind of follows this curve. And so we see that the specific volume is relatively low, and therefore it contracts more in the exterior. So what happens with those two competing areas of the glass is that it puts the outside, the edges and the surface in a compressive state of strain, and then it puts the center of the glass in a tensile strain by having this sort of dissimilar cooling rates between the exterior and the interior. So the exterior cools quickly while the interior cools more slowly, resulting in this stress state. And so we can actually visualize this, this compressive and tensile on the interior with this type of tempered glass. This is actually a slightly different type of tempered glass, but it's the same idea, is that out here on the edges, so this is the edge of the glass on one side and on the other side, and then this would be the interior. What we see is that this kind of affected region with this optical kind of polarization that we see is this disturbance that shows us that the depth at which the compression results on the surface of both sides, and then in the interior, that's the tensile region that we see in the interior. So we have this interesting sort of stress or strain state. So the other example of this is Prince Rupert drops. So some of you may have seen us do this at various department functions, but basically what they are is we take glass, so typically we take a glass rod, and we take a very high temperature blowtorch, and we soften that glass rod until it becomes movable, and basically when it becomes liquid-like, it would naturally form into a teardrop shape, right, from gravity. And so when it becomes heavy enough, what happens is it drops, and it forms a teardrop or tadpole shape that you see here. And what we do is we let it drop into very cool water. So just room temperature water works nicely for this. And what happens is this is the same quenching effect. It's quenched in the water so that the exterior is rapidly cooled, and the interior, you can see here, this is an actual image from when we do this, you can still see it's molten in the middle, and so it cools much more slowly than the exterior. And so we create this thermal tempering effect in Prince Rupert drops, and you can kind of see the same type of stress state as we saw before, because we have relatively large specific volume compared to the interior. So we have compressive strain on the outside and then tensile on the inside. And so what this gives us is that this compressive strain increases the strength of the material, right? Because that compressive strain on the surface makes the material stronger, right? We saw that for brittle materials, glasses, ceramics, those materials are stronger in compression, and so the exterior is under a state of compression already, and so that kind of prevents any cracks that may be there from failing until we overcome that compressive strain. So that means that higher stresses have to be applied to that material before it breaks. So if you see videos, and I'll try to link the original video in this video, but what you can see is that when they test these materials, they're really strong, and you can actually hit them with hammers and they don't break. So these Prince Rupert drops. However, you can actually very easily break a Prince Rupert drop, and what you do is, and it's kind of hard to see here, is that the tail of this Prince Rupert drop, basically, if you are able to break that, so use some type of pliers or something to break that, what happens is all of that stored strain energy from the difference in the compression and tension causes that to be basically rapidly released, and it propagates down the tail and causes the whole thing to shatter in a large number of pieces. So I'll put the original video where these were taken in the comment section or in the description of this video. All right, so another way pretty well connected to what we just talked about with thermal tempering is ion exchange. And so if you're in the MSE 407 lab or have taken it before, this is exactly what we're doing. But basically the idea of ion exchange in a material is that you take the ions that are within a material. So in glass, this would be what we term those network modifiers in the silicate glass, something like sodium, is that we can actually exchange those materials, those free ions, with ions in external bath. And so typically this is a nitrate salt, a molten nitrate salt, heated to 300 to 400 degrees Celsius. And we have something like potassium out here. So we have potassium nitrate on the outside and sodium inside the glass. So what that looks like is, in terms of diffusion, that's a very large concentration gradient, right? We have 100% potassium out here, and then assuming our glass is mostly sodium as the modifier, very heavily sodium here, and then 0 or low percents of potassium. And so there's a driving force for potassium to want to go into the glass and sodium to want to leave based on the concentration gradient. And so if you give it enough thermal energy through diffusion, those two can exchange, hence the name ion exchange. And so you can see here that the potassium have taken the place of the sodium. So why this relates to strength is because, as you can see here from this cartoon, potassium is actually a larger ion than sodium ion. So if the glass is below temperatures in which we can relieve stress, like the strain point and so forth, then when we put a potassium ion in the structure, it will compress the area around it because it's larger than the sodium. So if it's not allowed to relax, then it will compress this area. And so when it exchanges, that area around it is in a compressive strain. And so that's the idea here. So it has to involve an ion in the glass that is relatively small to the ion being exchanged in the liquid solution, like the nitrate. And so that's the case of what we see with ion exchange. And this is the common phenomena that you see with Gorilla Glass that probably makes up your phone screen, is it's strengthened using this type of modification. And we see that the strain field here is similar and basically the same as thermal tempering. It's just done chemically instead of thermally, but they produce the same type of tempering on the exterior of the glass surface. All right, so the last mechanism that I want to walk through is known as the formation of glass ceramics. So this is a class of materials in which we actually now start with a glass. And so this is the temperature profile as a function of time of the processing mechanism. So we melt the material, we shape it into something like a cup, and then we cool it down to form the glass. And so that's how we, form and shape glasses. However, we go through an additional thermal cycle where we heat it back up to some temperature. And you can see the softening points somewhere around here. So we heat it up high enough where crystals of this material can form and nucleate. And then sometimes we'll even heat it up again from there to allow those nuclei or embryo to grow. So what we're trying to do is we're trying to, in a controlled manner, grow crystals of this material because those crystals end up giving it additional strength and toughness compared to the glass because we have essentially particles within the glass. And this allows us to take advantage of the forming capabilities of glasses with the strength and toughness of crystalline materials. So, this is, again, maybe on the borderline because we're talking about glass. Here, these glass ceramics are actually somewhat, at least partially crystalline in nature. And so that's an additional part to that. And some of these materials are like, some of the examples of this are certain Pyrex materials can be this glass ceramic. Sometimes the process is known as ceramine.